Warahmatullahi wabarakatuh, and my name is Muhammad Ashrahan bin Abdul Jalahan. My number metric was S70420. So today I will talking about chapter 6, numerical method for ordinary differential equation, ODE. An ordinary differential equation, ODE, is a equation that describes how the quality changes over time and space. It involves the unknown function and its derivative. ODE are used to many fields like physics, engineering, biology, and economy to model real-world phenomena such as mechanical systems, electrical circuits, and disease spread. Solving ODE analytically can be difficult, so numerical methods are used to find approximate solution. This method breaks the problem into the smallest step to compute solution over time or space, helping us solve the complex problem in the area like engineering, physics, and biology. For the next slide, we talking about the three methods that have in this chapter. So the first one is early method, and the second one is an improved early method, and the third one is a Rush-Kutta method. Each this method have a few formula that we use to find the answer or find the value of x and y.
Hi, my name is Muhammad Akimi bin Muhammad Lahadi. My metric number is S71135. I will continue with the problem statement A. Use Runge-Kutta method with a step size of h that is 0.5 to estimate an approximate value of the solution at x 0, 0.5, 1, 1.5 and 2.0 respectively. For the first part, we have formula represent. Formula for the fourth order Runge-Kutta method is yn plus 1 equals to yn plus 1 over 6 in bracket k1 plus 2k2 plus 2k3 plus k4 h. This formula used to numerically solve the first order ordinary differential equation ODE of the form dy over dx equals to f in bracket xy. The equation provides a more accurate approximation of the solution compared to simpler methods like Euler methods. Okay, next we will continue to the definition of K1, K2, K3 and K4. For the first part, we have K1. K1 equals to f in bracket xn and yn. This K2 equals to f in bracket xn plus h over 2 and yn plus h over 2 k1. This evaluate f in bracket xy at the midpoint. F in bracket xn plus h over 2 and yn plus h over 2 k2. Okay, for the last one, K4. K4 equals to f in bracket xn plus h and yn plus hk3. This evaluates x in bracket xy at the end point. Okay, for the next part is where the value of x and y come from. The first one, we have initial values. The starting point is given as x0 equals to 0 and y0 equals to 0.5. Okay, next we have step size of h. H equals to 0.5, meaning you increase x by 0.5 at each step. Okay, next we have subsequent values. Subsequent values of x. x1 equals 0.5, x2 equals 1.0, x3 equals 1.5 and x4 equals 2.0. The last part, we have subsequent values of y. These are computed iteratively using the formula for yn plus 1.
Hi, we want to find the y1, so we want to get the k1 node, k2 node, k3 node, and k4 node first. So right now I show you how to get the K1 node. K1 node formulas is equal to F bracket X node and Y node. So we get the X node is equal to 0 and Y node equal to 0.5. So we use the formula with Y negative X squared tambah 1. We can get the K1 node equal to 1.5. The second K2 node. How to find the K2 node? We use the formula with K2 node equal to F bracket X node tambah hash bagi 2 and Y node tambah hash bagi 2 darab K1 node. So we get the K2 node equal to F bracket 0.25 and 0.875. So we sub the question with Y tolak X squared tambah 1. We can get the K2 node equal to 1.8125. The third, we want to get the K3 node. K3 node formula is equal to F bracket X node tambah hash bagi 2 and Y node tambah hash bagi 2 darab K2 node. So we get the K3 node equal to F bracket 0.25 and 0.953125. So we sub the question with Y tolak X squared tambah 1. We get K3 node equal to 1.89062625. The fourth, we want to find the K4 node. We get the K4 node formula with F bracket 0 X node tambah hash and Y node tambah hash darab K3 node. So we get the F bracket 0.5 and 1.445313. We sub the question with Y tolak X squared tambah 1. So we get the K4 node equal to 2.195313. Last, we want to find the Y1. So Y1 formula with Y node tambah hash bagi 2 darab K1 node tambah 2 darab K2 node tambah 2 darab K3 node tambah K4 node. So we get the Y1 equal to 1.425130.
B. Find the percentage of error if given the exact solution for this problem is y equal to x squared plus 2x plus 1 minus 0.5 exponent x. Calculate exact value and percentage error. Use the exact solution y exact equal to x squared plus 2x plus 1 minus 0.5 exponent x. For each x, calculate error equal to y exact minus yrk over y exact times hundreds. Initial value problems. Y prime equal to y minus x squared plus 1, y0 equal to 0.5, step size equal to 0 equal to 0.5, exact solution y equal to x squared plus 2x plus 1 minus 0.5 exponent x.
The problem presented revolves around calculating the percentage error for mathematical function when comparing an exact solution to an approximate one. The function in question is given as y equal x power of 2 plus 2x plus 1 minus 0.5 e power of x. To solve the problem, the first step is to substitute specific value of x, namely x equals 0, x equals 0.5, x equal 1.0, x equal 1.5, and x equal 2.0 into the given function. This substitution allows us to compute the exact value of ys for each of these x values. Here, the numerator represents the absolute difference between the exact and approximate value, while the denominator normalizes this difference by the exact value, converting it into a percentage. Example conclusion. For x equals 0, the exact value of the function is calculated as y0 equal 0 power of 2 plus 2 multiply 0 plus 1 minus 0.5 e power of 0. So approximate 0.5. For s equals 0.5, the exact value of this function is calculated as y 0.5 equals 0.5 power of 2 plus 2 multiply 0.5 plus 1 minus 0.5 e power of 0.5. So approximate is 1.4256. For s equal 1.0, the exact value is compute as y 1.0 equal 1 power of 2 plus 2 multiply 1 plus 1 minus 0.5 e power of 1. So approximate is 2.6409. For s equal 1.5, the exact value is y 1.5 equal 1.5 power of 2 plus 2 multiply 1.5 plus 1 minus 0.5 e power of 1.5. So approximate is 4.0092. So finally, the exact value for s equal 2.0 is y 2.0 equal to power of 2 plus 2 multiply 2 plus 1 minus 0.5 e power of 2. So approximate is 5.3055. Next, when the exact value are determined, the percentage error is calculated using the formula, which is percentage error equal exact value minus approximate value divided by exact value multiply 100. So for x equal 0.5, the approximate value is given as 1.4251 using the formula for percentage error. So you can count like error equal 1.4256 minus 1.4251 divide 1.4256 multiply 100. So approach equal 0.0357%. So for x equal 1.0, the approximate value given as 2.6396. The percentage errors become 2.6409 minus 2.63 minus 6 divide 2.6409 multiply 100. So approach equal 0.0476%. Okay, for x equal 1.5 which an approximate value of 4.0098, the error is 4.0092 minus 4.0068 divide 4.0092 multiply 100. So approach equal 0.0583%. For x equal 2.0, finally, with the approximate value of 5.3019, the error is 5.3055 minus 5.3016 divide 5.3055 multiply 100. So approach equal 0.0729%.
So the next part is a table of percentage. Every each value in table of percentage we can get from the calculation slide before this. As example, x, y as pro, y as z and percentage error, we can get this value in the equation before this. So as example, x equals to 0.0, y approach equal to 0.5 and y as z equals to 0.5, the percentage error will become 0.008%. It is because we use the percentage error formula that error equals to y as z minus y approach divide by y as z multiply with 100. So we can get the percentage error there. So this is our table for our answer and looking for the percentage error. So the finally is a summary. In the summary, chapter 6 and we can call the numerical method ordinary differential equation is very important to essential for modeling dynamic system in science and engineering. Challenge to analytical solution and often difficult impossible for complex problem. In Euler method, simple but less accurate. And then improve Euler method, better accurate with moderate complexity. And the last one, Rush-Kutta method, high accuracy, suitable for many applications. This application we can choose as an example because the Newton law of cooling simulate a temperature change. Rush-Kutta method, it equals to the high accuracy because the temperature need a good care for the value of the temperature that we need to operate, not to be high, not to be low too. Thank you for them.